Hello everyone. Let's look at today's lit code question. So the question is 958. Check completeness of a binary tree. Okay, let's read the question. Check completeness of a binary tree. Given the root of a binary tree, so I'm doing this. I'm just saying this problem for the first time. Let's do it together. Given the root of a binary tree, determine if it is a complete binary tree. Okay, in a complete binary tree, every label except possibly the last is completely filled and all nodes in the last label are far left as possible. It can have between 1 and 2 to the power h nodes inclusive at the last label h. Okay, 1 and it can have between 1 and right. So it means that what complete binary tree is. So this is a complete binary tree because uh, because all nodes have it's complete because all nodes are filled, right? And one is also filled, but it is filled left from the left side. And 1 2 3, so this is obviously a complete binary tree. And 2 3 4 5, this is also a complete binary tree because everything is filled from the left side, right? But I think, is this a complete binary tree or not? Every label except possibly the last is completely filled. Oh, so it means that every label should be filled. So suppose if this was the case, 6, then this would not be a complete binary tree because the last one is not filled, but the second last one is also not filled, right? So only the exception is for the last label can be not filled. But even if it is not filled, then it should be filled from the left side. In the last label are far left as possible. So this is also this is also a complete tree, but this is not a complete binary tree because it is not filled from the left side, right? All the nodes in the last label are not as far as left as possible because this is the node in the last label, but this is not on the left side. If it had 6, so every label is completely filled, right? So this is a complete binary search tree, but and this would be a binary search tree because all the nodes are filled. I mean, all the labels are filled, only the last label is not filled. And the last label is not filled, but last label is an exception according to this question. Last label is not filled, but though it is not filled, it is filled up to the far left, right? 4 is filled, 5, this left right is filled, this is also filled. So suppose if it was like this, then it would not be a complete binary search tree because the last label, it is not, all the nodes are not in the far left, right? Yeah, but if there is no 6, then this is still a complete binary search tree because all the nodes in the last label, they are on the far left. Okay, so this is what binary search tree is, and it can have been in 1 to 2 to the power as nodes inclusive at the last label edge. It means that 2 to the power as nodes means everything is filled here. So this means that 2 to the power 2, right? Because the label is 0 here, 1 is 2 to the power 2. There are 4 leaf nodes, and it can have between 1 to 2 to the power h. So this is also a complete binary search tree. Okay, so I need to know if it is a complete binary search tree or not. This is true because every label before the last is full, right? And even in the last label, they are full. I mean, even in the last label, all the nodes are as far left as possible. And like I said in the example, in the example, this is not full because though all labels except the last is full, but even in the last, it is the 7, it is not as far left as possible. If it had, if 7 was left child of 3, then it would have been a complete binary search tree. Okay, and the number of nodes in the tree is in the range of 1 to 100, and node dot value, it can go from 1 to 1000. So it means that there is no 0 or negative value for node dot value, and the number of nodes in the tree can be It means that there is at least one node in the tree, and it can go from 1 to 100. Okay, let me think of brute force solution first. How to detect if it is all filled or not. um I think that I can. So my first thing that came to my mind is that I can do a BFS, right? So if I do a BFS, then if I know that the next label is not full, and that is not the last label, then I will return immediately false. But if I know that all the labels are full and the last label is not full, but the last label is, is filled from the left side. Suppose there is 1, 2 and 3, and I know that, suppose if there is nothing here and there is 5 here, so I know that 2's child is 4 and null, right? So there is 4 and null here. It means that this label is not full, right? If this label is not full, then if any label has a null child, then what should happen? Then all the other all the other nodes that come after that null should be null, right? So if this is null, then this would also be null. 3 child should also be null. But if I find that this is null, but this has some value, then it means that it is true. It is not a complete binary search tree. So whenever I encounter a null value, right, like this might be, so 2's left is null. So whenever I have a null child, then all the nodes that come after it should also be null. Otherwise, it is not a complete binary search tree, right? So this would also be null. So I encounter null here. So all 2's right should also be null. 3's left and right should also be null. If that happens, then it means that if this is not fulfilled, then it means that it is not a complete binary search tree. Otherwise not a complete binary search tree. Binary tree. And another thing is, so that is when I know that but what if, I'm just thinking, are there any conditions or not? So 4 5 4 5. So in this case also, this will detect, this will say that according to this condition, this will be a complete binary search tree, because if something is null, then everything will be that. And even for this case also, since even if for a full tree, also since this is null, so every child will be null. 4's left will be null, right? 5 left, right, 6. So if the label is completely full, then also this will be satisfied. And I think thus this criteria is enough to check if it is a binary, if it is a complete binary tree or not, because there can be 3 cases, right? First case 1 is everything is full, every label is full, and even if every label is full, then this criteria will be satisfied, because even if every label is full, then 4's left is null. So once I find something null, then everything is null, so this would be fulfilled, and we can say that this is complete binary search tree. And case 2 would be if a label other than the last label is not completely filled, right? So in this case also, suppose this is the case, then 6. Suppose if this is the case, then I know that 2 3, so there is 4 and 5, and there is null here. So there is null here, but since there is another child here, so I can say that it is not completely filled now. Yeah, so I think this is a quite straightforward, right? So if I encounter a null, then all the values that come after that should be null. If I encounter any value, then it would return false. So this case is also fulfilled. Here there is null, here there is null, but there is not null here. And case 3 is this case 4 and 5. Then in this case, case 3 is a only last label is not completely filled. Then in this case also it will determine. So since this is null, it force right is null, so everything should be null after that. Yeah, it is like binary breadth first search algorithm. Suppose this is x and y. So in breadth first search, so if I do a breadth first search in a binary search tree, not in binary search tree. If I do a breadth first search in a complete tree, then breadth first search would be continuously values only. So here it would be 1 2 3 4 5 x y and 6. So if there is a one null, then everything would be null. So in a complete tree, but in a non-complete tree, breadth first search can have null in between values. So there can be another null, and there can be 5, there can be null again, there can be 7 again. So in a non-complete tree there can be null in between values, right? So but in a complete tree there cannot be null in between values of this order. Label order traversal, this is called label order traversal, right? Okay, label order traversal, it cannot be, there can be null between values, but there can be null in between values in a non-complete tree. So this is our criteria, that so we'll just do a label order traversal, and we so solution each we will do a label order traversal, and if we find that there is a null, there is a value after null, then return false. Yeah, otherwise if we finish traversal, but still if we finish traversal but still there is no values after null, then return true. Okay, so this is my algorithm. Yeah, so this is my algorithm, and this would take O of n time. Algorithm, this will take O of n time, and the time complexity would be O of n, because I might have to visit all the nodes, and space complexity would be O of I think it would be O of n only, or O of how many, O of 2 to the power h actually, because I'll do label order traversal using q, and if I'm using q, then the most nodes that can enter in a queue is equal to a label, that is it is equal to the leaf nodes. So there can be 2 to the s leaf nodes, so q is to, okay, 2 to the h, where h is the height of the uh, tree. Okay, I think this would work, right? I'll just visualize again. So first of all, q would be 1 and null, so it would have some root, and then um so i'm I'm putting null, or I can just say, because the values would be from 1 to 1000, right? So I can just say, I just wanted to put a delimiter, but I think I don't even need a delimiter, right? Or do I need a delimiter? uh, I don't even need a delimiter, isn't it? Because I just wanted to put a delimiter, because I wanted to know that another label has come. But I think I don't even need that, because I do not want to distinguish between the labels. I just want to check if there is a value after a null or not. So yeah, so q is equal to 1 first, and then I will pop q, and when pop q, then there will be 1, and push one child to q again, right? So one child is 2 and 3, push 2, push 2 and push 3 to q, and after I push it, then I again pop 2 and 3. So I pop q and 2, and then push 2 child to q again. 2 child is 4 and 5, right? So this is how I'm doing label auto traversal. Now pop q, that is 3, and then I'll push 3 child to q again. So I'm popping q, so now 3 child is x and y, right? Yeah, now 3 child is x and y, and this is how I'm doing label of traversal. So 1 2 3, pushing, popping, and whenever I should also check the child every time. Check child of the front element from q. So this is I'll always pop front element from q, because this is q is first in first out, so whatever I enter first, that I will pop. So first of all 1 is entered, then 2 3, so 2 is entered, so first of all I'll check for 4 5, and then xy. So check child of front element if it is null, or not. If it is null, then I can raise some flag, okay, raise flag that null is encountered. So if null is encountered, then you know, so first of all flag null encountered would be, in the beginning it would be false. So whenever the, if child is not equal to null, if child has some value, then what I do is, if child has some value then if child has some value uh, and null encountered is false, right? If child had some value, or what I can say is, if null encountered is false, and if I have not encountered anything and child has some value, then it means that I'll continue. But if null encountered is true and child has some value, then it means that I found. It means that found value after null, which should not be there. So I'll just return false immediately, right? Yeah. But if null encounter is true and the child has not any value, child is null still, then I would keep on pushing and popping. So in this case, push 3 child to 4 5 xy, and then I would pop 4, and then array would be now 6 comma null comma 5 xy, right? So I pop 5 4, and then put fourth child, so it would be 6 comma null 5 xy, and and if it is null, then I would not even uh, put in the what should I say? If it is null, then I don't even need to put it in the queue. If child value is null, then don't put it in queue, because I'm putting in queue just to do a traversal, right? Because if it isn't doesn't if null doesn't if there is a null child, then I don't have to look at null child again, so I don't even need to put. So 4 is 6, and 5 child is both left and right, they are both null. So null encountered is true, but child does not have some value, right? So I'd continue looking that I'd continue doing that until queue is empty. Okay, so let's code now. So first of all, let q is equal to root, and then I'm getting a phone call. It went away. It stopped. So let q is equal to root, and while q dot length, right? So, and now first of all I will pop front. So q is this, and I'll also set let null encountered is equal to false in the beginning, and front element, what is the front element? I need to pop, right? So I can pop the front element using this q dot shift. So this will, if the queue has 1 2 3, then it would shift 2, and then it would return 1. So the root element would be returned in this case, and root element would be returned. So after the root element is returned, then I have to after I return 1, then I need to push 1 style to queue, right? So I will now look at fronts. If it has a left child, then I need to push it, and I'm just pushing its right and left child. So I also need to check for every child. I also need to check if it is null or not, right? So what I can do is, otherwise if it is not, if it is null, then this would be true, right? Otherwise this would be true, yeah. So if it is present, then I am pushing it to queue, but if it is not present, then I would say null encountered is true. Okay, so okay, and then I should also check if null encountered is true, uh, I should also check if, okay, how to do this. If null encountered is already true, first of all, before writing this logic, I will complete the code. Okay, I'll complete checking queue, pushing and popping in the queue. Then I will do this, write this code at last. So if front dot left, front dot right, I'm pushing to the queue, and okay, I think this is it. So queue, and then I'm popping the front. I mean, I'm shifting the I'm getting the front value, and then I'm pushing the values left child and right child. So push front front's left child to queue, and push push front's right child to queue, and continue doing that. Okay, so if null encountered is equal to true, and I think that, do I even need a null encountered true? Because there can be 7, and I think that I can only check if the what is the last value, right? I don't even need a null encountered value here. I think that I can just check what is the last value, because if I say that the last value that has entered the queue is null, I can just say instead of if any label has a null child instead of this one, it is similar to, if last value is null and, oh, or what should I do? Because this might be, I was just trying to see if, if this is null, and if this was not null, if this was it. I was just trying to check if the value, I was just trying to compare the current value with the past value. So if current value is has some value and past value is null, then I was thinking that would work. But yeah, I need to consider the whole scenario. So what should I do? There should be a continuous value. There should not be, how to test that there should be continuous values. There cannot be, values after null, right? There cannot be null and then it. So whenever I encountered any value, then yeah, I think this is good. So if null encounter is true and child has some value, then return false, right? So in this case also, uh, suppose here, so in this case child encounter, null encountered would be already true, right? Here in this case, so because force left is null. So if I get uh, 5 here, then there is a value. So what I should do is, after pushing it to left, I should check. I'm just reverting back. So sorry. So what I should do is, after if null, if there is a value, and if null encounter is already true, if this is true, then I need to return false immediately. And the same case here as well. If it is already true, so if there is a value in the left, if there is no value in the left, then this would already be true, right? So the same thing here as well. Yeah, I mean, I was trying to write a clean better code, but this looks so messy. And at last I should return true, because I have, because this means that I have looked at all the nodes, but still I have not found this. There is a value and null encountered true and true. This is really a messy code. Oh wow, it worked. Yeah, I was thinking to make this code better. How can I make it better? From the left, front left, I need to check front left and right. Let me look at the solution. um First one is breadth first search. There is no node in the given tree. If root node is null, we return true. And create a boolean when null not found to track whether or not a null, we initialize it to false like this. And if node is null, then mark null node not found true. But if it is not null, then we check to see if previously visited a null node. Oh nice. Oh how they're doing the same as I doing. I did not even check if root is equal to null, because they are saying that there will be at least one node. A solution. So while q is not equal to, so I first of all did this. While it is not empty, then q dot poll, it is similar to q dot this one. And if node is equal to null, then null node equals to true, null node found. Otherwise, if not null node not found, oh, time complexity, each q expression Each queue operation in VFS takes O of one time, and the single node can be pushed only once, leading to O of n operations for n nodes. Since we had directed edges, each edge can be iterated once. Okay, space complexity is the last or the second last label would have the most nodes. The last label can have multiple null nodes in a complete binary tree. Because we are iterating by label, the BFS queue will be most crowded when all of the nodes from the last label are in the queue. And assuming that we have complete binary tree height h, then it would be to the power h. So all the nodes at each label add up to 1 plus 2 plus 4 plus 8 plus 2 to the power h. Okay, which is equal to n. This implies that 2 to the power h plus 1 minus 1 is equal to n, and thus because the last label has 2 to the power h node, the BFS queue will have ON elements in the worst case scenario. I did not understand this completely, but they are just adding all the nodes that we are storing in the queue. So there will be 2 to the power h nodes in the final label, and in the first label there is 1 2 4 8, right? So the total sum from 1 to 2 to the power h is equal to n, because like they said, yeah, because this is true. 2 to the power h plus 1 minus 1 is equal to n. I mean, if we sum all of this, then it has to be equal to n, right? Because there are n nodes. Okay. And depth first search as well. So this, even for the depth first search, the space complexity and the time complexity is same. So the code here is even simpler because they are checking for the for if it is null or not only once. They are not checking for the child. So I can also, I think, change my code accordingly. So how can I change my code is, first of all there is 1, then 2, then 3. So this is a left child and this is a right child node. Okay, so what they are doing is they are only here. I'm trying to push the left child and right child whenever I find it. Yeah, so what I can do is, what I'm doing here is I'm not pushing a value if null is encountered, but what I can do instead of this is I can push it even if it is null or not. I don't care, I'll push it anyway. So it means that since I'm also pushing the null value, so it means that this front value can be null as well, right? So what I'll do is, if it is equal to null, then I will say that null encountered is equal to true, and otherwise if it is not null, then I will push left and right value, right? And so yeah, if it is null, then I will so I will check if the value is null only after popping, not while pushing. So what I did earlier was I was checking if it is null while pushing to the queue, but since I'm pushing to the queue 2 times, so that was too messy code. But I can just check if it is null here. Yeah, and if front is null, then encounter true. So if I can check if we have encountered, or if it is true, then it means that the value is not null, right? It means that, so there is null. So whenever I get null, then I will say that is encountered is true. So suppose I get 4 now when I'm looking at the queue. If I get 4, then if it is not null and I get 4, then I should return false immediately. Yeah, this is This is much more simpler code. Oh, what did I miss here? If null encountered is equal to true, then I should return false. Hmm. If it is null, then I said that encountered true. But if it is if front is not null, if it has some value, then I'm checking if it is false, right? So what that's what I was doing here. If child, or if it has some value, and I know that we have already encountered null before, then it would be written false. And then I would push q, that was from the left and from the right, and then I would again shift q. So in this case what would happen is, suppose this is the case, then first of all 1 would be added to the queue, 2 3 4 5 x y, right? And at last for 4 5 also null will be added, null, null, and x for xy also null will be added. So null encountered will be true, it will be true. So what's wrong here? I think this is fine. Yeah, that's what I did here also. I thought that this would work. 1 2 3 4 5 null 7. Output is true, but I should false. Obviously it should be false in this case, because in the beginning first of all it would be, oh, what am I doing here? I'm returning root first, right? So it would be 1 first, and there will be 1 in the queue, and 1 is not null, so I'll push 2 and 3, and then I'd push 4 and sorry, and then I'd push 4 and 5, and then for 3 I'd push, sorry, I'd push 4 and 5, and for 3 I'd push null and 7, and for 4 it would be null, null. So for 5 also it would be null, null. And whenever I get a null value now, it would be, if front is null, then null encounter would be true here, and so this will already be true, right? So whenever I'm popping 7, then it would go to this else loop, and since null encounter is true, it would return false. But why is it returning true then? One, two, three, four, five, six. 6? From that, oh, value, I can only do this here. So in this case it is 1 2 3 4, 1 2 3 4 5 7, and let's check if null encountered is true or false. Oh, even in 7 it is false. Why is that so? Because if it is 7, then when I'm pushing for 3, right, when I'm doing it for 3, then 3's left is null. So I should have, this would have, I would also print q every time. So in the beginning it is null, so yeah, in the beginning the queue is null, queue is empty, because I've shifted it, and then it is, and then I'm putting um oh, one. Why I'm putting three null and where's two? Okay, first of all, I think that I should do it here. So in the beginning, there is one, and then one is popped out, then there is two, three, right, and two is popped out, three is popped out here, then there is four, five, and null here. Five is popped out. I mean, why is, if front is null, then why is null found? Right, they should be null found. If it is null, then why is it not, like, null found false? So here there is null value here in Q, and it is shifted. In this case, the Q has a null in the front, and when we shift this, then there is null found and false. Why is it still false? Oh shit, oh my god, what the, I should do one. Oh my god, that was so funny. Oh, yeah, so I was doing double equal to, oh my god. So I think the code that I did was, um, the code was longer, and this is short and concise code, because I'm taking null just once only, not when I'm pushing it to children, but when I'm um, pulling it out of the queue, that is just once. Yeah, so thank you for watching, everyone.